Welcome to Homework 39, where we're going over problems 2 and 5 from section 9.8. The first one reads, a simple beam of length L supports a concentrated load at the midpoint. Evaluate the strain energy of the beam from the bending moment and the deflection curve. So from the textbook, we have these equations for our strain energy, one with respect to our moment and the other with respect to a deflection curve. And looking at my beam here, I can model my beam and cut it somewhere looking for some moment as a function of x. I have a reactionary point at point A, so I can solve for that, and then knowing that and having some distance away from wherever I'm splicing my beam, I can solve for my moment. Then I can plug that into my u, noting that this moment equation that I solved for only tells me the moment from A to L halves. So I can integrate from 0 to L halves and then find another one from L halves to L, or I can just know that due to the symmetry of this beam, I can multiply my first integral by 2, because it will be the same strain energy on both the left and the right side. So that's what I'm going to do because that's easier. Solving that out, I get this. Next, for my strain energy, I can look at the back of the book in the appendix, table H2, situation 4, which conveniently is exactly this problem. It has a V equation of E prime, but our deflection curve, so our V double prime, which is specifically what we're looking for because that's what's in our equation, it doesn't have, but luckily, since it's a simple derivative, we can just solve for that from our V prime, plug that in, and then simplify that out and get the exact same answer, which is what we wanted, because this is just proving that both methods are equivalent. Now, here I did an integral from 0 to L halves and multiplied by 2. I did not have to do that. I just did that because I did that with my moment. However, I could have gone from 0 to L and then not multiplied by anything, because my V double prime function is continuous throughout the entire beam, and you would have gotten the exact same answer. Now part C. From the strain energy, determine the deflection delta under the load P. So one way you can go about this is intuitively. If you recall, a long time ago we had that U equals 1/2 delta P, and then we can solve for delta, or if you were paying close attention when you were reading from the book, you would have solved this equation. They are exactly the same, it's just how you write it down. So if I have delta equals 2U over P, I can just plug in this U that I have, divide it by my P, and this is my answer. A simply supported beam with an overhang supports a concentrated load at the tip of that overhang. First, determine the strain energy stored in the beam. So, if we recall, we can use two methods. I'm going to use the method where we solve for a moment first, because although we probably could idealize this and then use equations from the back of the book, it is faster for me to use the moment equation, so that's what I'm going to use. So, I also know that my moments are going to be non-continuous because I have this B support in the middle of my beam. So I'm going to have to solve for my moment as a function of x in two locations. So starting with A to B, I have this setup going on where I can split it between A to B. I need to solve my reactionary A force. This A in my equation, AL equals P lowercase a, that A is just my reaction at A. Sorry for not being consistent there, but that's what that's supposed to know. I can find my reaction at A, and thus I have my moment. Now, for the next part, I need to know what my moment is on my other side. Same deal, except I already know what my force P is, so I can just find my moment from that. Then, plugging all of that information into my strain energy equation, I can do my two integrals, and this is what I get. From the strain energy, find the deflection under that load. So we have our same equation that we were using before, and it really is as simple as it looks. We have our exact same equation, but we're multiplying by 2 and dividing by p. That easy. Calculate the numerical value of our strain energy and our delta at C with the following numerical values. So we have an L, we have the length of A, we know the shape of the beam, so we can get our inertia. In fact, I'm just going to pull my inertia straight from the appendix. And I know the maximum stress. However, our equation, our delta and our strain equations are functions of everything that we just read, except it needs a P instead of a stress. So just real quickly, I need to convert my stress into a P value. So knowing that it's going to be a bending stress, I'm going to use MC over I, plug in my moment, specifically the maximum moment. We've had 2 moments that we solved for earlier, but since this is my maximum bending stress, I need to plug in the value where I have my maximum moment. Now that I have it symbolically like this, I have my sigma and my p. I just need to solve for p as a function of sigma and plug that in to both my delta and my u, and these are the answers I get once I plug in all the information from the problem statement and the appendix for my inertial value. Strain energy, and what is it? Hopefully you have a mild idea, at least, of what strain is, just because we've talked about it a couple times. Just as a reminder, it is the energy inside of a system due to the internal, not deformations, there are deformations that make up strain, but the elastic strain is specifically what we're interested in, which is the part that isn't deformed. But if you think of the atoms being squished together, they want to not be squished together. That is your strain energy. The elastic strain energy is when it hasn't deformed and it is still able to go back into its initial frame. And we've seen several equations for it. The new one that you will want to remember is simply put this one. Again, you can use your V double prime equation as well if you want to look in the back of the book. I think this one's more beneficial since if you look at the definition of how M and V double prime are related, the 2 equations are exactly the same. Really, it's just a preference of, is it easier for you to solve for your moment equation as a piecewise, or is it easier for you to look at a beam, figure out how to idealize it such that it matches your V double prime equations in the back of the book, and then plug it in? And because they're exactly the same, it doesn't really matter which one you do. But that's the equation, and that's really the only thing new that you need to know from this section. Alright, I hope this was helpful, and good luck with your homework.